I'll give the exam back at the end. If you have problems with it, come find me as soon as you can. I'll send the answer key out. I forgot to do it yesterday. I'll do it when I get back to my office. Check against the answer key, see if there are any mistakes, get that sorted out as soon as you can, and then we're getting ready for a final. We have 3 weeks now to cover a fair amount of material, but I would suggest that 22 is really the end of the really difficult stuff. And then 23 is a summary of a mean, some of which you've already done, and the rest of that stuff, the end chapters, I always summarize in sort of a brief and try and make some context. In terms of where we're at, we're in 22, we're talking about alpha carbon chemistry. This is tricky stuff. It was done reasonably well on the exam, but obviously there's a lot more to come before the final. The whole point of this is the idea of having an electron withdrawing group next to a proton. And if you have that situation, you can take off the proton because it's acidic. And we saw with the Aldol reaction, which you've done in lab and which you now know a bit about from lecture, that this is very powerful. It's very useful for putting molecules together by knitting together carbon-carbon bonds. And that's really it for the rest of the chapter here, is making carbon-carbon bonds. So what we'll do today is move into the later stuff, which is the idea of the Claisen condensation. And in recitation this week, there's no quiz, but I will spend all the time trying to differentiate between these types of compounds. Aldehydes and ketones do a certain type of chemistry, esters do a different type of chemistry. That's been a theme for about a month now. The problem is people get them mixed up. A lot of people lost points on the exam because they were mixing up carboxylic acids with aldehydes and stuff like that. That's important. The Claisen condensation, named after a guy named Claisen, obviously, is the equivalent of the Aldol reaction as applied to esters. So now we're starting off with a slightly different material, which you can make from a carboxylic acid or from an acid chloride, and we are treating it with a base. And that base then we have to be careful here in what type of base we choose, but we are going to be able to do alpha carbon chemistry here. Now, go back into the notes and look at saponification. Make a note of this. Just compare this with the saponification reaction, because we did that with a base and it went a different pathway. If you use hydroxide, you get saponification. If you change the base around here, you don't. You get a condensation reaction. And the key feature here is the fact that the base is often chosen to match the leaving group on the ester. Because even if the base goes after the carbonyl and kicks that leaving group out, you get the same molecule back. There is no change. So what we'll do here now is recognize that we have another place on the molecule that we can attack, and we know that as the alpha position, and we'll use the base here to go after that proton and do what we did with the aldol type reaction. Now, for reasons that should be fairly obvious, the protons on an ester are less acidic than for an aldehyde or a ketone. And the answer is, if you put a negative charge here at the alpha carbon, you have lone pairs on the other side pushing into the carbonyl, and if you have a lone pair here pushing into the carbonyl, that will be slightly less stable than if you had an aldehyde or a ketone, in which that does not happen. So the pKa for an ester typically is around 24, 25, but we can still deprotonate them and set up an equilibrium and make this reaction work. Mechanistically, very similar to what we've done. It's a nucleophilic acyl substitution process, but you've got to be very careful in terms of what decisions you make in terms of leaving groups or not. So at the bottom we have the alpha deprotonation. That's fairly obvious, and we get this. And again, I'd like to see a resonance structure, and that will describe why that thing is stabilized because of the delocalization in that molecule. And we get to this structure. What would you call that? Tetrahedral intermediate. If you're getting this stuff, it is just repeat. Yeah, it is a tetrahedral intermediate. That's fine. And those things have collapsed, and for the most part on the exam, leaving groups left, and I was quite pleased. My in-laws didn't show up. I was really pleased. It was a good weekend. So we lose the leaving group, and we end up now with a molecule that is similar to what we've seen before. When we did saponification, we ended up with a carboxylic acid, but it was produced in a very basic reaction mixture. So the carboxylic acid got deprotonated immediately. Now we have a system in which we have a proton in this molecule. This is a beta-keto ester. You'll be hearing that phrase a lot. In which we have a similar acidic proton. It's not as acidic as a carboxylic acid. Its pK is about 10 because it's in between two carbonyls, but it's not going to stop there. The reaction is going to go forward, and it's going to actually end up being pushed towards this molecule because of the acidity of that proton between the two carbonyls. And that will be a big theme between now and Wednesday, is using that in a chemical process. And at the end of this week, we'll be able to do all sorts of stuff in terms of 38 steps on a synthesis because we know all sorts of different chemistry. So be very careful here. This first process is nothing more fancy than nucleophilic acyl substitution. Then you get to deprotonation. That will happen regardless of whether you like it or not. It's going to come off. And the product of that reaction is that. And that salt could then be used for something else. What would you do to isolate that material? What's the first thing you would do in the lab next to be able to get this material out of here? Quench. Yeah, you have negative carbon. Salts are quite difficult to work with often, organic salts. So we'll quench it, add some acid, and we'll get our product. So to go between here and here, you can see the second step there is H+, and that's a quench step simply to put the proton back. And again, put an asterisk or whatever you use to differentiate, to highlight things. Compare this with the saponification. That's where the confusion lies. People get mixed up with the bases, they do the wrong thing, and it's definitely one or the other, dependent upon the base. So the Claisen condensation is really useful for making all sorts of materials. Again, you can knit 2 carbons with 2 carbons and you can get bigger pieces, and you can make 20 out of 20 and stuff like that, and we can make quite big molecules quite quickly. The quench step there is simply trying to get the proton back. Again, why do we want this stuff? Well, it's not a salt. It's an organic liquid usually, and you can distill it. It's easy to purify. If you left it at the salt stage, it might be tricky to work with. Now, I've just mentioned the saponification reaction. Here's the difference. You need to be careful when you're using the particular base. In this situation here, we have the saponification. We chose hydroxide as the base, and in this case, it's acting actually as a nucleophile. So yes, it can deprotonate at the alpha position, but again, we're looking to go to the best place. And in recitation this week, I'll do a whole bunch of things in which we go backwards and forwards in different directions, but ultimately we end up at the product. Why? Because that's the most stable thing you can get to. So even if you go down all these different alleys, you'll end up going eventually to the best product. So here we can see saponification from the past, giving the carboxylic acid, which is still in the presence of base at high pH, and inevitably gets deprotonated to give the carboxylate. That was the end of that reaction. If you choose hydroxide with an ester, you will get that outcome. If you change things and you use, let's say, methoxide in the presence of ethoxide, you're simply adding a bit more complication, because you will get exchange between the 2 leaving groups. If the methoxide kicks out and behaves as a leaving group, you'll get a mixture of the ethoxide and a mixture of the methoxide. And that just complicates things. So when you're designing these syntheses, you usually match the base with the leaving group on the ester. Sensible stuff. Okay? Now, this is the most difficult time of the year for most people. It's starting to get nice out. You have a lot to do in the next 3 weeks. Lots of grades are flexible at the moment. Could go up, could go down. That's entirely up to you. Stick at it, and stamina comes into play right now. On my website, again, I have some animation right here and some sort of talking over the slide, so you can listen to this again if you like. There's the nucleophilic attack of the enolate. Here's the leaving group taking off from the tetrahedral intermediate species, and then we deprotonate. And the final product from that first step is that anion. Now, I've drawn the resonance structures down here to be more complete. You can go in both directions here. You have a charge in the middle, which can spread left or right, because you have 2 carbonyls. So you've got to watch out for those types of details. And then finally, in the last step, you quench, and you get this. And this is a beta keto ester. Ester's obvious. Keto is obvious. Alpha carbon, beta keto ester. They will become really useful materials in a couple of slides to be able to make bigger systems. Okay. So we can also do cross Claisens. It would be kind of limited if you could just add 2 and 2 and get 4, but now you can cross Claisens. And the problem with the cross Claisen, just like it was for the crossed aldol, is if you use 2 enolizable starter materials, in other words, 2 starter materials that both have alpha protons, you will inevitably get mixtures. So you take care of that by starting out with something like this. This does not have an alpha proton. Okay, for those of you who are still putting 5 bonds to carbon, there is no proton right here. Okay, I would hope you'd be through that by now, but some people are still doing that. We don't have a proton there, so you cannot make an enolate from that. So what you choose here is one that does have a alpha proton, and then away we go. And we'll get a straightforward Claisen condensation, and we end up with a mixed product that we would then quench. Now, there is still a problem here. You think about this technically. If you were to deprotonate this and make that a negative charge, it's in equilibrium with the acid. It's in equilibrium with its conjugate acid. So in that mixture, you would have 2 esters and 1 enolate. So you can imagine the enolate can go after both esters. It can go after this with the molecule on the left, and it could go after this. So you'd end up getting mixtures. Now, how do you fix that? How do you make that work? Well, you could start using this stuff. What was LDA? Very strong base, and something special about it as well? Large, right? It's large, so it doesn't tend to attack carbonyls. It goes after alpha protons. So you can set this up in a clever way, if you like, to completely deprotonate your starter material so that there isn't an equilibrium here, that all you have is that. So you only have 1 enolate in the mixture now, and you don't have any of the ester left. Then, in a second step, in the lab, maybe through a syringe or a dropping funnel, something like that, you would add a second ester. And then that allows for a fairly clean process in which you attack only the 1. So again, be careful. The product of the first step is the negative charge. It is the anion. You then have to quench it to be able to get the material out that you want. It's a very, very useful reaction. Well, Claisen reactions, we'll do a bunch of these things in recitation, but you can also do it in an intramolecular sense. Intermolecular reactions are fairly straightforward, and I did like seeing this when I was grading the exams. People are getting used to the R group. You have some big ugly thing that 99% of it doesn't change, just circle it and call it R. And then you just have to organize the sort of business part of the molecule that is changing. That was fine. And you'll see here now that the only difference in the molecules that you'll see is the different R groups on the ends of these molecules. That's all it is. It's the same Claisen reaction again and again. And of course, the best way to make money in this business is to take an intermolecular reaction and then invent the intramolecular version. And that's what we call the Dieckmann cyclization. So the Dieckmann cyclization is just an intramolecular Claisen. That's all it is. And you'll start to notice now on my problem sets for the later chapters that if you have two functional groups in the molecule, then you can often get cyclization. If they're too close together, you often cannot get cyclization because the cycle will be too strained. If you have one functional group like a carbonyl in a system, it won't cyclize. You'll get an intermolecular reaction. You can make fairly straightforward decisions based on that type of idea. Now, I have a molecule over here which has two esters, one at each end. It's symmetrical, so there's no problem here in terms of what's going to happen. It doesn't matter which end you take a proton off. We've chosen the base appropriately to match the leaving groups. There are no complications. And then we're going to quench after we do the cyclization step. But what's going to happen now is I'm going to deprotonate either here or here. And they both happen to be the same in that molecule, so there's no concern about which end we attack. If we deprotonate, we make the enolate. The enolate is resonance stabilized, but it then goes after the other end of the molecule and it cyclizes. And that's shown in this step here. One end is the nucleophile, the other end is the carbonyl. Now in this system, we get a 5-membered ring. That's fine. What do you think about 4-membered rings? No, you're probably pushing it there. Other things might be better than a 4-membered ring. Certainly 3-membered rings. Other things should be better, and we should go backwards and forwards and end up in that better place. And obviously the best one will be 6. So you'll find this is a very useful way of making cyclic compounds from now on. Example again, there's from the website. It's the same thing, but with more detail in terms of the actual outcome, in terms of the intermediates, and in terms of their resonance structures. We have an alpha proton with a pK of about 25. You can take it off. Even if you only get a small amount of this stuff, it will then become a nucleophile, and it will attack. And this is what you're doing. You're counting 1, 2, 3, 4, 5. Just count the alpha carbon, count the carbonyl carbon. Whatever's in between them, there's your cycle. In that case, 5. An extra CH2 group would be 6-membered ring. It's as simple as that. Again, I need resonance structures to show why these things are available, why they're allowed. Again, we then get the cyclization attack. Fast or slow? Intramolecular reactions. Fast. Why? It's there. Nothing more fancy than that. Everything's already there, right? It's right there to attack. Instead of going and finding it, it's right there. So we get the tetrahedral intermediate. This then collapses. There's my beta-keto ester. But be careful here. That's not the product yet. You have this situation where this proton now is acidic. It's about 10 pKa because it's in between two carbonyls, and so it will come off. So the last step here, because we are still at high pH, and I would say of the 78 people left in the class, about 68 people understand pH. 10 people just don't get it. All right? In this case, you're at high pH. This is basic. Any acidic proton will be taken off. Take it off. So now we get deprotonation here. We end up with this. Why is it allowed? Because it's very good in terms of stabilization because of the negative charge delocalizing into 3 different places. That then gives us the product. What is the product of this reaction? The first step, that is the product. That is the same molecule just represented as different resonance structures. Then to get this out of here, we have to quench, and we get this. And what you will notice is that that is this. Okay? Don't be lazy here. Don't just stop at that point. That's only half the problem. That's missing the point as well. So be very careful. Questions, anybody? Stunning silence. Right, okay. Moving along, because I want to get through this chapter, because I want to get into the special topic stuff at the end. Well, we dealt with aldehydes and ketones, and we said we can deprotonate them, and we can form enols and stuff like that and behave as nucleophiles. And we had some questions, actually. I think Tricia asked this question about the idea of the regioselectivity. I think Kristen asked a similar question. What happens if your system is biased? What happens if your aldehyde and ketone is not symmetrical? In fact, let's stick to ketones because aldehydes can't be symmetrical. In this example, we've got a fairly simple molecule like cyclohexanone. And we're introducing a base. We're choosing LDA in a solvent like THF or ether, which is polar aprotic, and we're going after an alpha proton. Why doesn't it attack the carbonyl? Because it's big, right? That's the whole point of that base. So it goes after the carbonyl, and it takes that proton off. And we said that the pKa of a proton in that position is about 19, 20, something like that. So if you use a powerful base like LDA, what is the pKa of its conjugate acid? High. High is the answer. Any ideas what number? What type of base is LDA? These details are killer. Go on. 38. It's a nitrogen, right? It's not delocalized, so it's 38. So that tells you it's not an equilibrium. That tells you with a pK of 20, 21 for the acid and 38 on the other side, it's going to the right-hand side. So you're going to end up with a solution that contains just this, the enolate. Now that's a nucleophile. We're going to see these things as very powerful nucleophiles, and if we add in the second step, maybe by syringe, some electrophile like methyl iodide, we can get an alkylation. Anybody want to tell me what that is? What reaction? It's an SN2, yeah? It's a very simple SN2 like we've seen before. Again, let me remind you, all the alkylation chemistry you'll see in my class is at carbon, not at oxygen. Even though the charge can spread onto the O, it's not a nucleophile in our realm at least. It might be later, but not here. So we get very simple alkylations, and now we have a system which we do have some bias. The R group on the right-hand side makes this molecule no longer symmetrical, and so maybe we can get some interesting chemistry through that. And that's exactly what this is telling you. Now, we're about to do some discussion of, again, thermodynamics versus kinetics, and how you can control reactions by setting them up in different ways. Low temperatures, short reaction times tend to favor kinetic processes. Longer reaction times, high temperatures tend to favor thermodynamic processes. So you can actually manipulate what you want in the mixture. So we have a system here in which this new material that we've just made is able to be deprotonated in two different places. I have two protons on the left, I only need one of them, and I have one proton on the right. Now, which do you think is more crowded, left or right? The one on the right. So maybe that's the slower approach. Which one gives you the more stable outcome? This one over here or this one over here? The one on the left. Why is this more stable on the left? It is more highly substituted. The alkene is more highly substituted. Go all the way back to Zaitsev. So we need to worry about what the base is. The base is going to be our pathway to be able to take off either proton. If you have a large base, which do you think is going to be more preferred? Attack on the left up here or attack on the right? Left. Right? So that's the very simple idea of steric environment. But if you want to set up something where you want this as the major product, maybe you're going to set up an equilibrium. So that's what we'll do. We'll choose some bases. Now, in terms of those definitions, and they will come about again in this chapter, and certainly in the later chapters, and then in biochemistry, what really is kinetics and what is thermodynamics? So kinetics is all about the height of these barriers. It's all about rates of reaction. Thermodynamics is all about how low those values are, how stable things are. So if we have a situation here which has two possible protons to come off, if I just put these on here now again, one on the left, one on the right. Which of these two curves, the red or the blue, matches the left-hand proton? The red one, yeah, the red curve. It's faster because that proton's more accessible, so the activation barrier is lower. We've seen that before when we did the HBr addition to 1,3-butadiene. And the slower reaction here actually gives us the more stable product. The slower reaction, again, is based on the fact that this proton is less accessible, so that reaction should be slower. But when you actually take that proton off, you get to the more highly substituted alkene, so therefore that should be the more stable product. So in this case, the kinetic and the thermodynamic outcomes are very different. And that's good because then we can control the reaction and make it do what we want it to do. This is setting up biochemistry, I would argue. You've got to worry about things like enzyme kinetics. These ideas are fairly simple once you get them, but you have to get them now. So here's how we do this. We are going to set up two experiments and get two different outcomes based simply on the type of base we choose and also temperature. On the left-hand side, we're choosing LDA. Why? It's a large base. We'll make it in dry ice acetone. We'll put a bath underneath the flask. We'll cool it down in some acetone, add some dry ice. That gets you to negative 78 degrees. And that will favor deprotonation at the left-hand side because that's more accessible. The large base is going to get crowded out from the right-hand side. Once we take that proton off and we make the enolate on that side, the second step is to alkylate, as we just have, and you get alkylation here. Now, this is a classic problem, and it's fairly well understood. But these reactions, you know, they're important in terms of developing things like pharmaceutical chemistry. You've got to be able to have chemistry like this to be able to functionalize these ketones. Now, that was all about irreversible, and it's all about coming to the more accessible place on the molecule. On the right-hand side, what do you tell me about this compared to LDA? Small. Small. It can get places that LDA can't. So in this case, we prefer to deprotonate on the right-hand side, and that gives us an enolate over there, which happens to be more stable because it's more highly substituted, and then you alkylate again, and you get as the major product the alpha-alpha disubstituted. Not alpha, and this is alpha-alpha prime over here, and this is alpha-alpha. So we have some really useful technology now to be able to build systems. We can do Claisen reactions, Aldol reactions. We can alkylate next to carbonyls. We can start to build materials like cholesterol. We'll start talking about steroid synthesis in a little bit. So this is powerful stuff and very, very useful. Conditions that you need to be aware of, you're looking for some enolizable materials such as a ketone. You're looking for a base. And the nature of that base dictates what happens. Big base, You get some regioselectivity, you get irreversible processes. Small base, you're going to get maybe the one that's the enolate that's more stable. So in this example, I'd simply have LDA again, THF as the solvent, polar aprotic, negative 78 as the reaction conditions. I will get the enolate on either side here, it does not matter. It's a symmetrical system. And after that is formed, I'm going to get alkylate at the carbon here, and that's the alpha functionalized ketone. Simple SN2 chemistry in the second step. The only difference you will see on the upcoming tests and exams and whatever is the nature of that will change, and the structure of that will change. Different R groups. In terms of this molecule here, what do you think limitations, what limitations apply there? Can I use a tertiary system? No. What tends to happen with tertiary systems in the presence of bases and nucleophiles? Elimination. Secondary you can get away with, right, sometimes. Primary are great. Methyl is great because they're accessible. SN2 chemistry obviously is preferred at more easily accessible places. So down at the bottom I have a more complicated system in which I put a methyl group on already. I have some bias now in the system. I've got a left and a right proton which are different. And LDA will come in. And which do you think it will prefer, left or right? Left, because it's more accessible. And then we'll do an SN2 on that. Benzyl bromide is very good at this. And we get 52% of that and 7% of that. Where's the rest of it? Distillation problems, column problems. You know, things often don't add up to 100%. So now we've got some way of defining where we put the groups. That's useful, that's powerful. And really that's one of the big themes at the end of this chapter is where do you put things and how do you design a system to put the group where you want it. So moving along. In terms of ester chemistry, we can also do this. And a very, very useful, this is classic old organic chemistry, but it's still very, very useful, is this old problem about differentiating between different types of proton. You know, 52 and 7 isn't great, is it? You'd rather have 100 and none. If you're trying to separate things, you'd rather have them biased in a better way. And we can get some of that idea here with this malonic ester. This is diethyl malonate. Every organic lab has a bottle of diethyl malonate. I can't find mine, but I know there's one in there. And this is cheap. I mean, we say cheap as chips. This stuff is, they give it away. And it's very, very useful for doing selective chemistry. And over here, what we'll see now is we're going to end up with a carboxylic acid at the end of all this, which has two R groups on the same carbon. We're going to alpha-alpha alkylate. And we're going to take advantage of the fact that between these two carbonyls, we have a fairly acidic proton. And we have two of them. So maybe I can take one off, alkylate, and then take the second one off and alkylate in an iterative sense, doing the same thing over and over. That will give me this, which is the alpha-alpha disubstituted material. And then, somehow, you'll like this one, I get rid of this group by heating it up with acid, and that gives me a carboxylic acid. So I'm taking advantage of the fact that the protons on the starter material are quite acidic, and much easier to take off than, say, an ester proton. You put it between two carbonyls, much more acidic than it would be just next to one. So diethyl malonate, you'll like this molecule. Very, very useful. How this works is fairly simple. There's just a lot of it. We have diethyl malonate, liquid, smells nice. Put it in the flask, put the base in. Why choose ethoxide? Why not choose methoxide? You don't want any complications by kicking out the ethoxide. You don't want to make mixtures if you can help it. So we'll deprotonate and we'll make this. And I want to see resonance structures, and there are two more resonance structures that need to be there for that molecule. Then this is nucleophilic. And that nucleophile, when we add an electrophile to it, we haven't put the electrophile in yet. We put the electrophile in next by maybe putting in some, maybe you'll put it in by syringe, something like that. And you get an SN2 reaction. And you get an alkylated product like we just did for the ketones. Except now it's between two esters. After that, we can either carry on and do that twice, or we can try the next step and get rid of one of the carboxyl groups. And this is a reaction that is interesting, and it is one of the few reactions that actually just involves heating something up. The Diels-Alder reaction was like that. You just heated things up and they flaked and they reacted. This reaction simply just involves heating things up, and then we're going to lose a molecule of carbon dioxide. So there is a lot embedded in this reaction. This mechanism is not trivial. There's a lot in here. What we're going to see first is an acid-catalyzed ester hydrolysis. We have done that as an individual reaction. We're now putting things on top of each other and just making the mechanisms bigger. So the whole process here, deprotonate, alkylate, they were just SN2 reactions after acid-base reactions. Now what we need to do with our R group installed is get rid of the ethoxy groups. So what do you think is the first step if you have some acid around? Oh yes, we do. We protonate, and most people do that, which I like. We'll protonate a carbonyl, we'll go after the carbonyl with water, we'll get a proton transfer, we'll lose the ethanol group, and we'll end up with 2 carboxylic acids at each end, one at each end. Okay, a 1,3-dicarboxylic acid. Now, if you heat this stuff up, it turns out that these types of molecules are thermally labile. And you'll see in biochemistry, this also happens there. The transfer of carbon dioxide between different molecules is really important. In this example, we're going to heat things up, and this usually is quite high, maybe 150, 180 degrees, because what we're going to do here is break a carbon-carbon bond. And that's a strong bond, so it's difficult to do. And it only happens if you have one carbonyl next to a carboxylic acid. You need that second carbonyl for this to work, or else it won't. So you heat up a typical carboxylic acid without that carbonyl, it won't fall apart. You have that carbonyl there, it will break apart into smaller pieces. And the way this works is quite unique and quite fun. If we heat it up, we get a carboxylic acid. So somehow this piece of the molecule has been chopped out. And I have this left over. That becomes carbon dioxide. Now this step is irreversible. Once you go to that product, it's not coming back. What do you know about carbon dioxide? It's a gas. As soon as you make it, it's gone. So it's out of the equilibrium and it's gone. So this irreversible step is simply a matter of heating up the molecule after you've got rid of the ethyl groups and getting to the beta carboxylic acid system like we have here. Now what's happened between those two pictures, this one at the top and this one here, is simply a bond rotation. All that's happened is that this bond has been rotated around. It's very again in restation. If you do that, you set this up in a conformation that allows for communication between the proton on the end and the carbonyl group. What's that called? Hydrogen bonding, right? These two are going to hydrogen bond between the carbonyl here and the hydrogen on the carboxylic acid. Now that's fine. That works at room temperature. That might affect the infrared spectrum, for example. But if you heat this up, we get this remarkable reaction happening. We get a concerted decarboxylation, a thermal concerted decarboxylation, in which a molecule of carbon dioxide is cleaved out. But that's only going to be able to happen if you've got some help. And that help comes from the carbonyl next door. A carbonyl is not there, it doesn't work. The carbonyl next door is able to hydrogen bond to this hydrogen, and in effect, it's behaving like a base. The oxygen is behaving like a base and going after that proton. And then we get what we call an electrocyclic reaction. We didn't do a lot of those, but they're all out there. An electrocyclic process in which all the bonds form and break at the same time through a 6-membered ring transition state. And if that happens, we end up with our carbon dioxide being broken out, and we get this, and that is an enol. And what you'll find confusing from now on is you get an enol, and you forget to go back to the carbonyl. Because the carbonyl is typically more stable, you have to go back to it once you get to the enol form. So the outcome of this is not this enol. It is actually the carboxylic acid through tautomerism. What we have now is a very clever, very elegant way of alkylating at the alpha position and ending up like this. So the malonic ester synthesis, important. Not so difficult in its individual pieces, but it's starting to add up. And that's a real problem now. In terms of what we can do with this, away we go. We promised 38 steps at some point. We'll be there soon. We can do very simple 7-step processes. Now you can imagine a one-page mechanism type question about this, or you can imagine a roadmap type question to be able to think about the final. And we have simply set this up so that we have 2 protons here. That's the key. We can take one of them off with a base. I'm choosing ethoxide again because it matches the leaving group. It will give me an enolate, which then goes after the alkyl group, do an SN2 reaction to alkylate. There's the methyl group being added. And in the second step, we take a base to take the proton off that material, and then we add a second R group, in this case ethyl. That's where the ethyl group came from on the left. What we'll do next is, in this case, we'll do the saponification reaction. You can do it either with acid or base because they give the same product, the carboxylic acid, and you get saponification followed by a quench. And then you heat this stuff up, and I'm going to give you an idea of about, what, 180? That's quite high. Because you need to break that carbon-carbon bond, that's not easy. And that gives you an alpha-alpha substituted carboxylic acid. This is great on large scale, very cheap material to work with, works very well, very high yields. It's all based on the enhanced acidity of having those 2 hydrogens next to those 2 carbonyls. That's really all it is. It's the same stuff we've been doing for a while. Anybody? Okay. There's my website. There is a step-by-step approach to this, talking about deprotonation. Again, choosing the right base. Alkylate on one position, take off the second proton, alkylate again. Saponify in this case is the idea here of using a hydroxide. And then we quench to give you the dicarboxylic acid, and then we heat it up, and that gives you the outcome. I don't think that's any more complicated than what we've done. It's just adding it together. And it will be on the final. You know it will be. One more exam left, that's it. Anybody? Okay. So there is an analogous thing called the acetoacetic ester synthesis. I'd like to get through this one today so we can finish this chapter on Wednesday and move on to the amines. This is another example of using these protons between two carbonyls. You'll see now that the protons down here, this is not the same material we just started with. This one is a beta-keto ester, which you can make yourselves. You can start out with an ester, you can start out with an alcohol, make a carboxylic acid, make that into an ester, turn that into a beta-keto ester, and then start doing this chemistry on top of that. You can go a lot of different places now with these reactions. We've got a base, we've chosen that again to match the leaving group, take a proton off, make an enolate right here, alkylate. In this case, we're alkylating once, and then we're doing this. Now, I will be maybe a little bit more sort of, give you a few more hints than that. H3O plus and heat, right? So H3O plus and heat may be acid catalyzed, maybe it's a saponification if you like. I'll give you more clues to that. That doesn't really tell you an awful lot, but that's how we do this. And again, in this case, we're getting rid of the carboxylic acid because we have a beta-keto part, and that gives you this type of outcome. Now, I have that on my website in more detail with that type of example. Same system, except we don't have the second carboxylic acid over here. We don't need it here. We still have the keto part, so it still does the decarboxylation, but we don't have that OH group. First step is the same. So learn it once, you don't have to learn it twice. Second step is SN2 to alkylate. Third step, deprotonate again. Fourth step, alkylate again. So now we have this more complex material with two R groups at the middle position. You can then either saponify, either H plus or base. Both of them work. If you did H plus, you get straight to here. If you want to do the saponification, you get to there. And that is a choice about what else is in the molecule. If something's acid sensitive, you have to use base. If something's base sensitive, you have to use acid. That'll be fairly simple. Once we're here, decarboxylate, same mechanism, and we end up with that material. It's exactly the same, other than the fact that you're missing one hydroxyl. Same outcome. Again, very powerful because you can make quite different things. I've been promising 38 steps for a while. People have been bugging me about the 38 steps. Where is it? When are we going to get to it? We're getting there. Here are 11. I think 11 steps is kind of good because that tells you whether you're understanding things and whether you can handle this stuff and whether you can handle the next level. Don't forget this is a prep class for biochem and things like that. First step, what's the product from the first step? Carboxylic acid. What's the product from the second step? Ester. Then we get the beta-keto ester. That is not a lot of information there to tell you that you're doing a Claisen reaction. It's how you have to study and you have to be on top of this stuff. That is a Claisen reaction. Doesn't tell you an awful lot there, but that's what the outcome is. Then we get the quench to give the proton back, and then we're going to do the sequence of deprotonation, alkylation at the alpha position. So we get two of these groups on here, and then we're going to finish off by saponification, and finally we're going to knock out the molecule of carbon dioxide. So that's 11 steps, but individually we've done each of those steps at some point. We're just now putting it together into a bigger picture so we can make it more useful. And this solves a problem. This reaction, even though it's 11 steps, solves a real problem. You've got a system here which has two different R groups on the same alpha carbon. That's not an easy problem to solve otherwise. The selectivity there isn't great. So this allows us to be selective. They're all very high yielding processes, and so it works very nicely. Anybody at the back? Any questions? Okay, carry on. Examples, how to use this. Here I have some simple starter material. This is methyl acetate, and we are taking that and we are turning it into the ketones. And so you need to be careful here in terms of what we use. I would argue that for this, what do I need here? What type of, I'm adding this and I'm adding this. So at some point I need to have ethyl bromide and I need to have methyl bromide. What do you think's happened down here? How do you get that? Tyler, anybody? John, Lauren. I'll go through all 78 names until I get an answer. You've got to have something like this. You've got to have some dibromide. I need 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 bromide. Okay? If you attack at one end, you then set up the second attack to be intramolecular, and you can make a cycle. That's powerful. So using those dibromides, which you can make from dialcohols, which you can make from cycles, through ozonolysis, stuff like that, you can now get to some very complex materials. Michael? It's on a primary system again, so the SN2 is preferred, isn't it? Because you get the carbon-carbon single bond as opposed to a pi bond. Yeah, so it does work. So we've covered a lot today, and there's the book to look at this in terms of what you can do with this. I'll ask you to design a molecule. Look at the stuff on the problem sets. Look at the old material that I've put out there on the website. There are lots of examples of how to use this stuff, how to put it together to use this and put big molecules together. Not done yet. So be careful here. This is no more complicated than where we've been, but you can't take the foot off the gas at this point because it'll be a problem. So with it being Monday, with Wednesday to get this finished, I think I'll start this now, give you a few minutes, then we'll do it again on Wednesday. This is quite different, and this is confusing. The Michael reaction. Michael. Professor Michael. This is a very, very useful way of selectively putting carbon-carbon bonds where you want them in an alpha-beta unsaturated system. And what we need to start off with is an understanding of how we got from here to here. This was pretty much the exam question, right? One of the exam questions there was simply take an aldehyde and couple it together to make a alpha-beta unsaturated system. And you should be able to do that mechanism in your sleep by now. Maybe some of you do them in your sleep, I don't know. What do I need for this to work? Give me some conditions. You need a base, you need some heat. And that will give us this guy. Now, the chemistry of this is all based on its electronic properties. The fact that we have a carbonyl next to a pi bond tells you it's conjugated. And that conjugation now is sort of important because that oxygen is electronegative. When we did this with 1,3-butadiene, where the O wasn't there, we didn't really do this type of stuff because that molecule was nucleophilic, not electrophilic. You put the carbonyl there, all of a sudden this molecule becomes electrophilic. And you should be happy with that delta plus right there, because we've spent 2 chapters on that now. Nucleophiles will go after that carbon. But there's more sort of added interest on this molecule because of that situation. You have a pi bond next to this. So the resonance structures at the bottom are very key, very important. There's the one where you just draw the whole thing as a neutral system. Here we can see delocalization of the carbonyl towards the more electronegative O. That then looks like an allylic cation. Go all the way back to earlier stuff. That double bond next to that plus charge, that's an allylic system within this overall molecule. I can then delocalize again, and I can get this. So the outcome now is that I have 2 delta plus carbons. If I wanted to draw this in a bit more detail, I'd argue that the beta carbon is also delta plus. The alpha carbon, no. The alpha carbon always has enough electrons. It's the beta carbon that becomes positive. So now I have a choice of places to attack. I can attack at there, and I can attack at there. And I think this is more realistic in terms of where we need to be for biochem. Molecules that have multiple functional groups, and the chemistry happens in certain places. You dig yourself through all the noise, and you just do the chemistry where it makes most sense. So with that in mind, there is the big thing for Wednesday. This idea of alpha-beta unsaturated systems in which I've got 2 places to attack. And I want you to read this before you come in because it can be very confusing. It will depend upon the nature of the material you put in there with that molecule where things go. With Grignards, we're going to say this is going to give a 1,2 product. With cuprates, we're going to get something called a 1,4 product. And that outcome is very similar to what we've done in the past, but we're switching roles now. We're attacking with nucleophiles, not with electrophiles. Same ideas, just switching the roles. So Wednesday we're into that. I guarantee I'll be into 23 on Wednesday because nobody wants to ask me any questions.